So far we've discussed supervised learning and we kind of concluded with supervised learning, both classification and regression in high dimensional feature space using a tool called kernel, right? Now I am not going to go further into the Mercer's theorem and reproducing kernel Hilbert spaces as far as kernels are concerned. I am going to leave that as optional study material for you. I kind of alluded to it in the pre-midsem part. I talked about the Mercer's theorem, but I realized that I don't want to make this course too theoretical because you have to be able to attempt the lab sessions. So I'll be posting those slides. What I'm going to do is help you appreciate that regression and classification, both of these, you are provided a yi for each xi, right? In training as well as test data, there was instead of saying provided, there existed so there exists a yi. In the case of regression, yi was real. In the case of classification, yi was either 0, 1 or plus minus 1. So this is basically, the setting is basically called supervised learning. I'll deal with two examples of unsupervised learning, and unsupervised basically means that you don't really have the ground truth yi's associated with xi's. You are basically given xi's. What can you do with xi's? Okay. So in contrast, you are provided only xi's. The examples could be like this. Let's say xi1, basically x1, x2. Okay, and these are the different points. This is an xi. Two-dimensional space. What can you do with this? Is a question. Okay, so the first thing is something called dimensionality reduction. That's one treatment. And what this will entail is as follows. So I'm going to give you a bird's eye summary of what this will entail. So in dimensionality reduction, when you are given these points, let's say I give you these points. Let me take an extreme example. If these were the points, okay, unlike the points here, these were the points. There's no yi. This is just the first coordinate x1 and the second coordinate x2. I visualize these points. What do you say? What strikes you? Yes? x1, well, it's not necessarily 45 degrees, but what probably strikes you is a relationship between x1 and x2, right? Some relationship, and statistically we refer to this as correlation. Have you done correlation coefficient? So this is a correlation, a linear correlation, for example. It need not be linear. We'll see that linearity, again, thanks to kernels, we will break away with linearity also, but correlation, some relationship correlation between x1 and x2 to be captured, and that is the topic of dimensionality reduction, capturing this relationship or correlation. Okay, we'll do that, and then we'll look at clustering, which is another view of the data. It says, well, instead of correlating the variables x1 and x2, I'll try and identify groups of the points. So what clustering does? Again, a bird's eye view. As the name says it all, if you see that points are grouped together, you can try and discover them. Again, these points are grouped together without any affiliation with the y. It's basically purely the first component x1 and the second component x2. And what you notice here is that there are two groups. So clustering is about discovering these groups. And both of these are about unsupervised learning. Do you get the high level picture? Any questions on this? I hope it's clear to everyone that in both these settings, we are not depending on yi. There might be a yi associated in clustering. There might be a yi that I have hidden from you. So for example, if you are kind of told about the demographic or let's say I give you characteristics of ants. You see ants walking around. I give you characteristics of ants. Now it's possible that the ants have an inherent classification. We all know, for example, just by the looks of it, you have big ants, small ants, and red and black ants, right? There are also white ants. So by the looks of it, they can be classified. But let's say I don't tell you the class label, actual class label. You can cluster them. And in retrospect, somebody may come and tell you, oh, by the way, this first cluster, it might have a label y1. The second cluster might have a label y2, plus 1, minus 1. But that's incidental. Any two labels existence is incidental only. So we'll first delve into dimensionality reduction. Okay. So dimensionality reduction, one of the very, I would say the well-known techniques is PCA, principal component analysis. And then we'll quickly see how you can kernelize PCA. Okay. So there is something called Occam's razor. It says that all other things being equal, pick the simple solution. So for example, when Occam's razor is applied for model selection, you will say, well, if linear models are fine, just go with linear models. That's Occam's razor, right? I mean, you could have a polynomial fit even when the data is linear, but then you subscribe to Occam's razor. So, I mean, it doesn't require to be told, that's what we do, right? Hostel से यहाँ आना है तो कोई hill घूम के तो नहीं आता, hillside घूम के नहीं आता. You just take the shortest route. So that's again intuition. So we follow Occam's razor in our life, and we do that even in machine learning. Pick the simplest solution. I just want to again highlight. You pick linear model unless the data cries for non-linear models. So why is simpler better? Can you give me some reasons why you come to your class not by going around hillside, take the shortest path, right? So you want to save time. So here in terms of machine learning, you want to save both the training time and inference time, right? So any other reason? You have done the bias variance decomposition training. So we want to generalize to avoid overfitting or to generalize. Anything else? These are good enough reasons. Let me know if you come across more reasons. So dimensionality reduction is one feature extraction technique which says, well, if your data could be represented with fewer dimensions and thereby subscribing to Occam's razor, why not? I don't need x1, x2 for this. Somebody said, well, if x1 equals x2, I just pick one of them. But it might just be that x1 is say alpha times x2, some alpha times. Or it might not be exactly, it might be approximately alpha times x2. That approximate, how approximate, that's what PCA will deal with, right? But if this is the case, do I need two dimensions? One dimension is sufficient. So Occam's razor, applying Occam's razor, you will say, well, my data should be written as x1 comma alpha times x1. I really don't have two dimensions, I have only one actually. So I might as well just say x1, right? And we'll see, you can rotate now. Basically, instead of you can consider this to be your x-axis and just consider the whole data to be one dimensional, right? So we'll see how that rotation can be implemented, but this is one way saying that, well, there is only actually one free parameter here, x1. The other is not a free parameter at all. So this is where Occam's razor comes in. As few dimensions as possible. Now this also is connected to something called VC dimensions. Again, I have pushed it as optional reading material. I have made the slides available. So VC dimension is basically how sophisticated is your classifier. It's a measure of the sophistication of your classifier or your regression model. So linear versus non-linear, we've been talking about it, right? What basically we are saying is how, given any class combinations, right, on the class assignments to the data points, for how many kinds of data points can I ensure that I am able to perfectly separate them in the model space for all possible class assignments. Okay, that's about VC dimension. Again, it will be a digression, but so VC dimension for the time being is basically the strength, how strong is the classifier. Is a classifier space of classifier models. Okay. So basically by reducing dimensions, we are able to, as you will see, I mean making the data more compact, we are trying to befriend even simple classifiers. Typically we will see there's a relation also between dimension and VC, I mean the dimension of the data and the VC dimension of the classifier. So again, I've left that as optional reading. So what dimensionality reduction is about is just discovering the true intrinsic dimension of the data and keep this canonical figure in mind. So fewer dimensions means it's potentially easier to learn and lesser chances of overfitting. So this is also, this again is loosely related to VC dimension. So let's start with, let's actually unfold the whole process. Are you able to view this from behind? So let's say we have an input example X and we want to reduce its dimensionality and project it to a k dimensional vector Z, where k is much smaller than d. Okay, so let's for the time being assume that the data is in 3 dimensions. X1, X2, X3, okay, and here d equals 3. But suppose the points I have got, they lie in some plane, 2-dimensional plane. Okay, the points are all lying in this 2-dimensional plane. Okay, so this basically suggests that I could discover these hidden dimension with k equals 2, d equals 3, but k equals 2. Is this clear? This is what we are relating to as d and k here. So let's write this a bit further. So these are my original points X, and I am going to try and transform them. Okay, so these points are somewhere here. I am going to say I am going to discover this U1, U2. That U1, U2 is exactly what corresponds to, that's what helps me define this plane. Also let me mark these on the U1, U2. I am drawing them separately. Now the same set of points which earlier had 3 coordinates can now be mapped to this 2-dimensional space . And these are what we refer to as Z. If this was an X, if this was an X, I am now projecting them into the space defined by the U's, and the projection is called Z. Okay. And the way Z is obtained is U transpose X. Now U transpose X, we have done this before. We have done this in the case of linear regression. Remember? We talked of this projection. Phi transpose 5 inverse phi transpose. So I mean you know that this corresponds to The Z is going to lie in the column space of U transpose, right? Is it column space of U transpose or column space of U? U transpose? Okay, and what are the dimensions of U? Let's mark that as well. So U is a D by K projection matrix. Okay, so U1, U2, UK. This is what U is. Okay, in this case, as I said, K is 2. Well, actually, now I want to ask you: is this U or are we dealing with U transpose? I'll revisit this question in 1 or 2 slides. Okay, so we will try and map whatever we are discussing on the slides to what is on the board. One more property I need of this U. This U is what is going to help me transform, right? So one more property I need of this U. So we will fill this up. So we also will like that U transpose U is identity. I've done that a bit implicitly here. What we want is that their dimensions are orthogonal, right? And I've done that implicitly here. And this, you could think of this as also subscribing to Occam's razor in some form. Keep the transformed space as simple as possible. The transformation process is also as simple as possible. So we insist that U transpose U is I. Okay. So again, I'm going to do a simple illustration. I will do the simple illustration after just finishing a little bit more discussion. So question is, how do you find that U? How do you discover this U which will help me reduce the dimension? What are the objective? What is the possible objective that you will try and optimize? So before I get there, how do you think you'll be able to? I mean, can you try and reconstruct an approximate X in the original space from the Y in the projected space? How do you do that? So I have basically gone from U to Z using U transpose X, and I have told you the dimension of U. What's the dimension of U transpose? Is K cross D. Now suppose I go back from this smaller dimensional space to the larger dimensional space, K to D. Let's call this X tilde. X tilde is U transpose Z. Is it well defined? Z was in R, K, X was in R, D. Sorry? Sorry, yes, use it. So X tilde can be a point reconstructed in the original space as U, Z. What is the relation you would like between X tilde and X? Okay. So again, I am summarizing this here. So in my original 3-dimensional space, I had these points nicely lying on some hyperplane. Here the points x were in R3, d was equal to 3. From this, I try and discover a two-dimensional coordinate system which will be obtained from the original space, but the points will now be projected onto the space. And these were z equals u transpose x. Z was in R2, here k equals 2. Right, and this is the process of transformation. And now I am asking you, what if I do the following again? So, my transformation was z equals u transpose x, but now I say x tilde equals uz. Sorry? So you would like them to be the same. Will it be the same? Why won't it be the same? So good, very good point. I mean, you would like it to be the same, and under some ideal conditions you think it will be the same. What is non-ideal about it? That it may not be the same. Because features are correlated. Because features are not perfectly correlated. If features were perfectly correlated, if you had this relation that x1 is alpha x2, then I think you probably have no loss, right? But is this exactly true? It's approximate, right? So please note that this doesn't hold exactly in reality. Now when I go back, so now my points may not be exactly there, it may be off. The x tilde may not match x exactly. Because correlation was only approximate. Is that clear? So but now try to, so her point is u is orthogonal, identity, u transpose u. What is the dimension of this I? So her point is, if I just do u transpose u,
you're getting x equal to z, you multiplied u on both sides on that. But u transpose need not be I.
Yeah, u transpose need not be I. So it will not be, so you got the point, right? So the other issue is, no, u is not square, I is square, but the dimension of I is what? What's the dimension of I? K cross K, it's not even D cross D. So note that as well. This is okay. So even if you don't get all these details, I mean, if you get the intuition what I've written on the board here, this intuition, you should be good. Is this intuition clear to everyone? I've used some u transpose to go to a smaller dimensional space, k dimensional space. I try and recover in the d dimensional space using pre-multiplication with u, and I'm a bit lost here. The green points, they don't coincide thanks to this cycle, because the correlation was never exact. Even approximately, that's why I always showed this kind of small variation around the correlation. Okay, so now can we define the problem? What is it that we want to solve? Yeah, so require TS to go around. I want now students to suggest what should be solved. In words, I am not asking you for mathematical expression. What should be the relation between x tilde and x?
As equal as you can make it.
As equal as you can. But you have done linear regression. What does it mean to say as equal as you can? So one suggestion is make them as equal as you can. In linear regression also we wanted y to be as close as possible to pi x. And what did we do in linear regression? Least square, sum of square, error. So could we do something similar here? Yeah, there are other ways also you can see. So you can look at cosine distance between. So his suggestion is look at a dot product between x and x tilde. Okay, so some normalized dot product between x and x tilde, that's another thought. But then that's about maximizing. Dot product you want to maximize, right? So we will see another perspective, very interesting point you raised. So we'll see two different perspectives of this entire problem. Good point. So one is a maximization perspective, maximizing correlation, maximizing some kind of association between x and x tilde, and the other is minimizing the square distance. Okay, so let's build on perspective 1. Minimize sum of squared distances of x tilde from x, where x tilde is as expressed here uz and z is u transpose x. And as rightly pointed out, u transpose may not be identity at all. U transpose u is identity, u transpose we will see that later. So it's talking about the second perspective. It's not, it's exactly not what he said, but the spirit of that we'll see. Okay, so let's finish this first perspective. Okay, so this is the step. So the whole idea is minimizing reconstruction error, and what we are talking about as reconstruction here is reconstruction of x tilde as x, right? So we are trying to make x tilde as x, that's a reconstruction. Okay, so the idea is first project down x to z, then reconstruct x tilde or x hat, right? And then now tell me what's the third step? Minimize summation over all the x of x minus x tilde x hat, whatever, x hat square, and this is minimization with respect to what? U. Let's put it as argmin. So I want argmin over u, but then I should write everything in terms of u. So I'll substitute for x hat as u transpose x square. Yeah. Yeah, but it's also related to pseudo inverse. The question is, why are we not looking at the inverse of u? U is first of all not square matrix, right? So if we had perfect correlation and if u were a square matrix, then this should have hold, because we are talking about u being orthogonal. So otherwise it's an approximation. It is turning out to be an approximation. because U is giving you a way of going back project. So U transpose you have to accept. So you accept is a way of projecting back to the original space. It is, I mean, because the dimension, right? What is the dimension of U? D cross K. Just by its dimension, it's a way of projecting back. We are not arguing that it's optimal way. We are saying PCA does this. I am just stating what PCA does. PCA says this U matrix itself could be used to project back if you had perfect correlation, right? Then it'll actually, so that is what it's banking upon. If the correlation were perfect, if all the points were lying along only actually this plane, you can show that U is good enough to go back to the original space. But that's not the case. So that's a deviation. Now whether there are alternatives, yes, there are alternatives. PCA is not the only way to go. But this is what PCA banks on. Foot. Okay. Yes. Yeah. So this is giving you one way of, so basically projecting back, and you're looking at one particular dimension. That's what he's referring to as foot. But I mean, let's understand it at a broader level. Not everyone in the class might relate to everything that we are discussing with respect to geometry. Right? So U is a way of projecting back. It may not be the best way as argued, but it is the best way if there was perfect correspondence. That's the only point I want to argue here. Or a best way, not necessarily the best way. So let me just highlight this point. UZ is the best way of projecting back into RD if the correlation were exact. We said that correlation was only approximate, but if the correlation were exact, U was sufficient. Is that correct? I mean, is that making sense to everyone? Okay. So now basically we have completed our introduction to PCA. So let's okay, so argument over all U such that U transpose U is I, argument over all orthogonal matrices of dimension D cross K. Okay. So this is the, I mean it's figuratively, this is what it says. It says that I have RD, I try to compress it, let me call this RK, okay. So RD, you try and compress it to RK and then try and reconstruct that back in RD, and that's X tilde, and you want norm of X minus X tilde be minimized, square field. This is the story of PCA. I think we try and explain it in multiple figures so far. But now I am going to try and give you another perspective. And the other perspective is also more computationally feasible. Somebody may ask you, oh, how am I going to solve this problem? डर लगता है ना, I mean, U transpose U should be I, you have some already vector में हालत हो जाती है, you're talking about matrices, right? So my appeal to you is, when you write the problem, don't get scared about how you will solve it. First, understand whether the problem makes sense, right? It's kind of appeals to your common sense, and then we will see how to solve it. So it turns out that there is another perspective. So there is another perspective which is maximizing the variance of projected data. Okay, now I'll explain it very intuitively. Okay, so this is perspective 1. And now look at perspective 2. I'll go back to this figure. And let's say these were the points. Now, this is more related to what we began with. We said the dimensions are correlated, right? If they are correlated, is there a way I can find the direction of maximum correlation? The direction along which they are maximum correlated. And then the direction along which they are next maximum correlated. And then the direction along which they are next maximum correlated. Can that help me discover my U? Right, so U now, I mean, so far U didn't have too much semantics, it was just that it's some coordinate system. But now I'll say, well, can this U be discovered by looking at the direction of maximum spread? You can think of spread, correlation, you can also think of variance. This is the direction along which the spread is maximum, right? This is the direction of max spread or variance. Spread is, we also talk about it as variance. So can I find the direction of maximum spread and then the direction of next maximum spread and so on? That's the second perspective. So we'll assume that the data points are centered to begin with, which means that we have shifted our coordinate system a bit. So we'll say that the points are all mean 0, because then it becomes easier to talk about correlation. Correlation becomes directly related to covariance, right? So I'll just center the axis here. So expected value of X is 0. That's the first point I did. As I said, my points were all here. I've just moved my coordinate system here so that Ex coincides with 0. Then I can talk about variance in this coordinate system. So now you compute the variance of the projected data. Okay, now I want a U. I will now project, like before I will project, but now I am trying to give you direct meaning to U. Okay, so the variance of projected data is expected value of the norm of U transpose X square. I mean, all of you know what is the definition of variance, right? Variance is sum over all xi of xi minus E of xi whole square. But then E of xy is 0. And here we are not talking about xi, we are talking about zi. In the projected space. So E of xi is 0, the projection also will get, I mean, U times x, if you take the expected value, you still get 0 for U transpose times x, right? So you are going from x going to U transpose X, which is Z. So the Z is also going to be mean 0, centered around 0. So this is nothing but summation over Zi of U transpose times Xi. But now you will talk about norm square, because you are dealing with multiple coordinates. And now instead of talking about, variance of course will require summation by n. So instead of talking about all of this, I will just say variance is expected value of U transpose X norm square. That is variance. Expectation will take care of the division by n. Is that clear? If you require, again I will write this. All I am saying is this is 1 upon n, where there are endpoints, of summation over I equals 1 to n of the norm of Zi minus expected value of Zi square, which is 1 upon n summation I equals 1 to n of norm of Zi square, which is 1 upon n summation I equals 1 to n of U transpose Xi square. Okay. This is what we are trying to look at, and we are trying to find the direction of maximum spread or variance. So now we are saying that this U will basically correspond to arg max over all possible other U's, etc., etc. You have to do this progressively. So find the direction of maximum variance, then the direction of next maximum spread, and so on. Okay, so this becomes objective. Max over U, U transpose U equals I of expected value of U transpose X norm square. Okay, is this more intuitive in terms of U? What U starts making some sense now. And now if I start writing down the U's, right? I did that earlier, but let's say I write U1, U2, UK. So we are saying that U1 corresponds to the direction of maximum spread, and therefore U1 might turn out to be here. This might turn out to be U1. And then the next maximum spread is U2, and we want U2 to be orthogonal. And it might turn out that U3 is basically 0, you don't have any more spread after capturing these two. Okay. So it turns out that minimizing, now I have given you some geometric intuition, but it turns out that minimizing the reconstruction error is actually equivalent to maximizing projected variance, and I have just referred to it in tutorial 6. So what we are saying is this, U is argmax U transpose blah blah blah, this is the same as this problem, right? They are two equivalent problems. The perspective 1 and perspective 2, they should give you the same solution. This is my perspective 2, this is my perspective 1. Okay, I have explained it in words here. So another perspective to PCA is that it finds a rotation of the original coordinate system in the form of some P is a rotation. I have just given this rotation a name. You have rotated this using some P and expresses the points in that system P, so that each new coordinate expresses as much of the possibility of the variability in X as can be expressed by a linear combination of the entries of X. So it's based on some linear combination only. I mean, there's a linear transformation. You're not doing any non-linear transformation, right? To do anything non-linear, what do? What name do you shout? Kernel, right? So that will come soon. So linear we'll do, and then non-linear we'll chant kernel's name. So it will come and help us, right? So now this has very interesting applications. Data transformation, as you can see here, we have transformed the data into a low dimensional space. Just complete this. Feature discovery. You're discovering which features are important, what combinations of features are important, and feature selection and so on. So many applications. Yes. Yeah, so that's a good point. His question is, how do you know that we have to progress only till k steps? Why not k plus 1? Why should k not equal to d? So that is a little bit of engineering trick. So you'll keep, and when I talk about the algorithm, you'll realize, because what does not, I mean, let me ask this question in response to your question. I mean, what does this remind you of? Do you know anything about matrix decomposition where there is something called the first principle, the second principle, the third principle? Have you heard the word, the adjective principle? Principal eigenvector? The first principal eigenvector, the second eigenvector. I mean, if you sort the eigenvectors by the magnitude of their eigenvalues, what does eigenvalue represent in terms of the eigenvector? So it's this. This actually gives you the. That's why I said it's. Gives you a very manageable form. The manageable form is that you do basically an eigenvalue decomposition of this U transpose X. Find the first principal eigenvector that will correspond to this direction. By say first principle, I mean the magnitude of the based on the magnitude of the eigenvalue. Second one gives you the second one, and so on. Now, as a recipe, you can check. Oh, whenever the eigenvalue becomes very small relative to the previous eigenvalues, I might drop. Okay, so I'll just make a note here, and then I will discover the algorithm. Okay, so this is related to eigenvalue decomposition, and that's why we are interested in it. Okay. Yeah, so that's what I was trying to show here, right? Expected value of norm of U transpose X is basically this 1 upon n times the summation over all the points of U transpose Xi, which turns out to be U transpose Xi is Zi, and which is nothing but Zi minus expected value of Zi. The rotated coordinate system also expectation is 0. So we are dealing with the variance here, not the covariance components. Okay, so now just to kind of again give a graphical view of the second perspective, this is what we are doing. We are saying that these points are all here, but instead of sticking to our original space, which could have been like this, and not exactly here because we are doing a mean 0, right? So we will say, let's say the space was like this. These are the original coordinates, and now we are saying we will rotate it. The rotated coordinates will look like this, such that this new rotated coordinate, you can call it U1, is direction of max variance. And what is the variance? You can see the variance is now being computed along this direction. I mean, the point he was trying to raise. We are not looking at correlation. Variance is variance captured along the rotated U1. So please try and understand. This is what amounts to our variance. Okay, so I'll highlight it here. Okay, so these are the variance components. sum of these squares along measured perpendicular to the direction u1, the intended direction u1. That's what we are referring to as variance here. Oh, I'm sorry. Yeah, you're right. So the measurement is along this direction. You're right. This is the direction of maximum variance. These are the error terms. Okay. Yeah. So I mean, if you want analytical proof, I mean, we can take it in tutorial 6. It's just a little bit of transformation. But I hope you get the geometric intuition. I mean, I hope you understand that both the solutions geometrically seem to be coinciding, right? Whether reconstruction minimization requires you to actually capture the dimensions of maximum variance. Reconstruction error minimization. Okay. So to find one principal component, this is what you do. You would maximize u transpose x square, the expected value, with u norm of u equals 1. Kind of you just unfold it, because now expectation will mean you do this for every x. So that's nothing but 1 upon n u transpose capital X. Okay, what is capital X here? Capital X is row x1 or column x1? Column x1, right? Column x1, column x2, column xn. Okay, right? So now if you just expand this further, u transpose x, x transpose u. This is the form you get, right? And we have just factored out this part separately, x transpose. Do you guys get excited when you see x transpose? Okay, so some of you are. Now x transpose also turns out to be, under the mean 0 setting, turns out to be the covariance matrix of the data set. X transpose is covariance matrix, right? PCA is not dealing with covariance directly, it is dealing with the direction of variance in the rotated space, but X transpose is the covariance matrix. Again, I am not going to derive this, but it is very simple. This is since expected value of x was 0. Otherwise, in the tutorial 6, I give you a more general expression of this covariance matrix. Okay, so now my perspective 2 has a very, very specific form. The first principal component u1 is max over the norm 1 vector space of u transpose 1 upon n xx transpose u. Made a small mistake here. This is 1 upon n. So this is an important finding. So S is the covariance matrix of the data. Okay. So now it turns out that this first principal component is really the top eigenvector of xx transpose, 1 upon n xx transpose, with the largest eigenvalue. Okay. So as I said, related to the eigenvalue decomposition, but now we have come to the real eigenvalue, I mean the really determining step. Okay. So this u1 is the largest eigenvalue of 1 upon n xx transpose. I mean, this is by definition, right? You know that the eigenvalue decomposition has to do with this quadratic form, and you will find that the lambda 1 u1 is going to dominate in this quadratic expression. So this is by definition. Again, we will If you are interested, go and read back a basic book on linear algebra. But this is one view of the largest eigenvector of a matrix, right? So think of this entire thing as S. The largest eigenvector of S gives you U1. Right? I mean, this is just again a graphical depiction. So these are x1 and x2 coordinate systems. This is x1, this is x2, mean 0. Mean 0. And then now when you compress it, I mean this has lot of some kind of noise around it, but when you compress it and make it really flat, look around x1, this is what you will get. I mean this is a very simple illustration. This is a compressed data, but it's also lossy. But this loss is minimal because we have captured the signal along the direction of maximum variance. Just to give you one more example, this very famous, very visually appealing. So eigenfaces, F-A-C-E-S. So let's say this was an original face, right? And now if you deal with the entire image as a vector, this kind of unroll the entire image into a vector and do this entire PCA decomposition. So you will find that, well, this face actually corresponds roughly to the principal eigenvector or eigenface, first principal component. First PCA component, then the second PCA. Okay, and you will find that, well, while first PCA, well, the weightage to this is very high, 0.9571, that is the eigenvalue. And intuitively it appears that this captures almost all the features, right? Major features that might strike you. Not non-intuitive. I am not saying this is the best, but this is not bad. So the first, if I ignore all the others, and this is very indicative of what the person looks like. Now in addition, if I bring in the other eigenfaces, the other principal components, I may be able to reconstruct more accurately. Okay. So this is basically your U1. This is your U2. This is your U3, U4. Now somebody asked a question, how much should I reconstruct? Now the images tell you a lot, right? I mean probably here first and second are good enough. I don't know how much value addition the third and fourth might bring, because their weights are also much smaller. The second one is just doing a small adjustment. The third is like already in the second decimal place. Okay. Before we talk about kernel PCA and its slight non-triviality, we have to realize the relationship between the data matrix X, its decomposition. So let's say X has a decomposition. So all of you are familiar with singular value decomposition. So see, so let's say X has a singular value decomposition A, D, B transpose, and let's say S is XX transpose, the covariance matrix, and S also has its eigenvalue decomposition. What is the eigenvalue decomposition of S? U sigma U transpose, right? So when we refer to the eigenvalue decomposition of S, we are basically referring to this form. Now what is the relation between the singular value decomposition of X and the eigen decomposition of S? This is very important to understand. What is the relation? If X is A, D, B transpose, S is U sigma U transpose, what is the relationship between them? Just equate components. What will be XX transpose? The SVD of X The Eigen decomposition of S will be linked through this, right? S equals X transpose. So what will be that? S equals AD B transpose times B D transpose A transpose, right? X transpose, you can write it down. Now what do you know about the singularity decomposition of X? What should be the form of A and B? Both A and B are orthonormal, right? I mean singularity decomposition, I mean I'm assuming that you have that background, right? So B transpose B is identity. So as a result this will be AD A transpose. So A is basic, I mean A, D and A transpose get adjusted as U sigma and U transpose. I mean the modulo the scaling, right? So there will be some, there will be D square. So you could think of U as being related to AD. Think of U as being related to AD. Is that correct? Okay. Now what we will do is look at the kernelization. In kernelization, the kernel gram matrix is X transpose X, as some of you rightly pointed out, it is X transpose X. Now can you expand X transpose X like we did for S equals XX transpose? What is X transpose X? So what do I do with X transpose X? Very similarly, I'll get AA transpose as an identity and I should get B D square B transpose. Okay. So this is the foundation of kernelizing. Now I'll give you the basic idea and probably the details you can try and work out in the tutorial itself. So this, yeah, I've kind of summarized it here. So U equals AD. What I have written on the previous slide is a matrix of principal component variables. Now with this, what you will realize is that you will not be able to directly recover U equals AD from the kernel matrix. I mean see the kernel decomposition B D square B transpose, right? That's I've kind of restated it here. Yeah, X transpose X is B D square B transpose. So you will not be able to recover the AD of the principal components of the covariance matrix from kernel. But what you can do, and that I have summarized here, what you can look at is the projections XU of our data into those components. That can be computed from the Eigen decomposition of kernel matrix. So kernel matrix, this is very similar to linear regression, or I think linear regression is the best case, right? We used a matrix identity there, but what we did was we didn't recover the weight vectors directly. We recovered the projection, the dot product between the weight vectors and the feature vector. So that's exactly what you are doing. I'll just write down that parallel. Okay, so we recovered the dot product using kernel. Similarly, the projections XU of the data X into the principal component space U can be, I made a small mistake here, so this is AD, right? So the projections XU of our data into those components U equals AD can be computed using the Eigen decomposition of the kernel matrix. This is the key idea.
So kernel PCA doesn't compute the principal components, it computes the projections of the data into the principal components, and that is the key. Okay, then I'll leave it to you to work out the details in the tutorial, the problem 2. Okay, this is a key observation. So you will compute the eigen decomposition of the kernel matrix not for computing the principal components, but the projection of the data into the principal components. That is it. So this is to give you the kind of direction for your tutorial problem.
So in tutorial 6, I've kind of given you this more general definition of principal component analysis in terms of a non-centered, so mean is not 0. So then what you can do is basically x minus Ex into x minus Ex transpose, take the expectation. So this you can do in tutorial, and I've taken a sample problem here where you're actually obtaining your points using some distribution. Right? We said expectation, but our expectation so far was with respect to the data. But you can do an expectation also with respect to an actual distribution. So I have left that in tutorial 6. That's a concrete problem where x1 and x2 both come from a 0 mean normal distribution with variance 1, and covariance matrix covariance value is theta. Find all the principal components of the random vector. So it will be nice for you to just do it once. I am going to just get started with clustering, and then we will basically delve more into it in today's lab as well as on Friday. What we have done so far is tried in an unsupervised manner understood the feature kind of compression, how features can be compressed, how they are correlated. But you could also look at points directly. As I pointed out in the beginning of the class, I give you these points, right? You can try and cluster them, and that clustering is also based on similarity. What similarity helped us find PCA and also kernel PCA, you can use similarity to also cluster points. So therefore similarity goes very closely with clustering. So this is from one of the older search engines. So let's say I gave you some some query keyword, keyword queries, and I think the query keyword was related to army. Okay, some army was a keyword. What we have done here is found clusters of the search results. You can also cluster query keywords themselves, showing what are very closely related. So cluster 1 consisted of certain keywords, cluster 2 consisted of certain other keywords. So these are query clusters of queries. So certain queries tend to co-occur. You might have seen when you are firing queries on Google, as you type some keywords, certain other keywords come up. Why do they come up? The keywords are probably being shown from similar clusters, right? Just because their results tend to be related. People who fired one type of query also fired the other type of query. These are determining factors. But do you think it's feasible for Google to actually treat it as a classification problem? Okay, this is class 1, class 2. How many classes can you actually generate for search queries on Google? It's not, I mean, and the new areas keep evolving all the time. So you have to keep changing the number of classes, and then you have to keep changing the classifier, the size of the classifier. It is not really practical. So clustering is very natural. I hope you can associate with this simple example of so scatter gathered as a text clustering system can separate salient topics in the response query keywords. So clustering, how do you cluster? Now there are multiple ways you can cluster. You can do bottom up or top down clustering. You can cluster for visualization, like PCA was also helpful in visualization. Now you can also characterize the entities. What are you trying to cluster? So you can look at, for example, similarity, dissimilarity between pairs of examples to cluster. So let's try and understand some of these points. So as I said, we are just given these points in some space. Now how do I identify a cluster? One way is look at pairs of points. So I may look at pair of points. Okay, these 2 points tend to be very related. These 2 points tend to be very related. So I can start with pairs of points and then cluster upwards. Okay, and this is the spirit of bottom-up techniques. I'll try and see if I can show you. So this is one kind of clustering. It's taking time to load. So nevertheless, what this bottom-up clustering does is it collects pairs of points, one pair at a time, right? And this is how it clusters. This is bottom up. What top down does, it says, well, I don't need to give start with pairs of points. For example, I'll associate a mean, 2 means. So top down says I'll start with these means, I'll put together points that are close to these respective means, and in case a point is very far away, I will adjust my mean. Okay, so the other aspect of clustering is, what are you going to use? Are you going to look at similarity between pairs of points or similarity between points and means, or are you going to look at distance? That's another characteristic of clustering methods. The third is number of clusters. I mean, here, just based on my visual instincts, I said 2 clusters. I grouped them into 2. But why 2? I could have had as many clusters as the number of points, which is meaningless, of course. But I want an abstraction which does justice to the points and at the same time does justice to my cognitive load. Because if you show me as many clusters as the number of points, I can't make sense of the data. And if you make everything into one cluster, saying sab kuch ek hai, so then it just defies common sense. It's not one, I mean they are actually 2. Right? So number of clusters becomes also a configuration issue. Why is there no straightforward answer to all of these questions? It's because we are dealing with a large number of noisy dimensions. I mean, text, it becomes very apparent, like query keywords. I mean, there are so many query keywords which occur very rarely, right? I mean, many queries are fired just before midterms, so Google doesn't figure out why these queries will be important at all. There are more other interesting queries people find in life, right? So there are large number of noisy dimensions or underrepresented dimensions. And the notion of noise is also application dependent, context dependent. Kernel could be a Linux kernel, it could also be our favorite kernel, right? A machine learning kernel. Now the notion is also context dependent. Clustering gives you a different way of viewing unannotated data or data in an unsupervised setting. So ordinarily, when you are given these points, you are not told what labels they have. Labeling is really an afterthought. So in some sense, clustering is more fundamental than classification. The labels carry some semantics. When I give a label to these, I call this +1 or -1, that's an additional semantics. Tomorrow that labeling can change, right? What is below poverty line? How many of you
know what is the latest definition of below poverty line. I know that Ahluwalia a long time back drew a lot of flack for his maybe somewhat careless statements, right. So the whole notion of below poverty line, whether it's X rupees per day or X plus 10 rupees per day, is something that keeps changing. But what will be always helpful in analyzing the income levels of people is the raw data. How much do they earn per day? How much is the variation in the amount that a person earns per day over a course of time, right? Average, min, max. These can help you characterize people even without people's incomes, even without the labels. But then how do you determine what are close and what are not close? And that's the whole subject matter of similarity measure. So you could cluster using similarity measure, you could cluster using distances. What is the ideal setting? What do you want close together? Those which have high similarity, right? And then distance, those which are far apart should be in different clusters. Now both similarity and distance, how do you characterize clusters themselves? So let's talk about two measures. One is intra-cluster measure, and the other which looks across clusters is the inter-cluster measure. So what would you like inter-cluster similarity to be? Okay, so inter-cluster should be low on rho, similarity measure, and high on delta. What about intra-cluster? Exactly the reverse, high on rho and low on delta. Okay, so it's important to qualify what you mean by high or low, whether it's within a cluster or across clusters. So if you think that this is below poverty line, then you want that below poverty line and above poverty line are very clearly separated from each other, have good distance between them, or are not very similar to each other. But those who are below poverty line should have similar features. Okay, and the number of clusters. I mean, let's again take this example of below poverty line. Maybe it's unfair to just talk of two clusters there. So sometimes the domain knowledge gives you an intuition on what the choice of k, the number of clusters, should be. And as I pointed out, many dimensions may be noisy, right? So for example, let's take the example of below poverty line. What would be a noisy dimension? Something that may not correlate well with whether a person is below poverty line or above poverty line. Hopefully not degree, right? I mean, I hope that degrees make some sense. But what else? Yes? When we say noisy dimensions, yeah, of course, height, you're famous, right? Height is a noisy dimension. But it is not that weight or BMI, body mass index, is completely irrelevant. If a person is below poverty line, malnutrition is a possibility, but then body mass index is also relative. It's not that people with low body mass index are necessarily weak, right? So there is a scope for noise there, right? So physical features can be noisy. Right, but more so, there might be a lot more other features which may be completely irrelevant. For example, the place a person hails from, where the person is born, right? So that may not be very useful at all. Demographic information. possibly age. Age might also be not correlating. It's sometimes inherited in a family. So how do you now filter out noisy dimensions? And now the noisy dimension is quite related to how well your rho or delta are also flexible. Okay. And as I also pointed out here, the notion of noise is application dependent. So from the point of view of below poverty line clusters, yes, demographic may be not very informative. But then if you are viewing the people's incomes from the point of view of potential to invest into an entrepreneurship, right, then possibly age might matter, right. I mean, I might have less money, but if I'm young, I might still want to take some risk with that money. So that's how the application would be very important in determining. So as I said, you can do bottom up clustering, you can do top down clustering, and I was keen to illustrate to you what this bottom up means. Here are some points on the x axis, I hope you can see them. Now what bottom up clustering does, you are going to just quickly see. So what you have done is, maybe the two points which are the closest have been clubbed together. And this is one iteration. Okay, so as I said, I can keep doing this iteratively, and at some point of time you have this dendrogram. Let's call it dendrogram. Okay, so now you can trace back the history. Probably these 2 points were brought together, then this, right? I mean, just by cutting at a level, you know what have already been formed by then. Right? So this was formed first, then this one, these two were the next closest, then these two. So what you are basically doing is computing pairwise similarities or pairwise distances, sorting them based on distances, right, and picking the ones closest to come together, except that the sorted list will keep getting updated. So for example, once I merge these two together become a candidate to be further merged. So these two have already formed a cluster. So whether I should merge these two next or merge this pair with a third one, that's a choice. But it turns out that these two are still closest, so this is next merged. And then this pair is merged with this one, oh sorry, these two are next merged, this is the third, but this next, and then this one, and then this one. Okay, so it's very easy to interpret. I mean most clustering algorithms are very intuitive, right? Now there are choices here. There's some parameters here, whether it's single linkage, complete linkage. It's a single linkage, complete linkage. The difference is largely whether I'll consider all pairs between two clusters or whether I'll consider only one. So for example, when I want to merge this pair with this one, right, will I consider the distance of this or similarity of this node with this one as well as this node with this one? Will I consider the max of them, the min of them? Now all those options start playing a role, right? So this is called bottom up clustering. Start from the points and then go up. Okay, so this is what I have tried to illustrate here. Now top down clustering is what you have in the lab, and that's where we'll spend a little bit more time. There are also other approaches, and I'll share these slides. So you have self-organization maps, multi-dimensional scaling and so on, but that's a lot too much for a basic course. There are also probabilistic models for clustering, like latent Dirichlet allocation became a very big hit in the pre-deep learning era. And basically the idea was, when I write a document, when I write an essay, I try and write the essay as a combination of multiple topics, right? So I have a distribution. Let's say you're writing an essay on machine learning and its application today. Now each of you carries a different perspective. Some of you are, as I heard, some of you want to do a project on reinforcement learning, even though it's not a part of whatever we have discussed so far. So you are carrying your prior information. So the topic, your latent topic influences the choice of words, right? And certain topics go together. So it's very unlikely that when you're talking about reinforcement learning, you bring in digital hardware somewhere, right? I mean, certain things don't necessarily go together very strongly. So topics, how they tend to co-occur. So that's how you create documents. So they have generative models, which give probabilistic semantics to how topics or clusters get created. But now we'll give the basic flavor of partitioning approaches. So the idea is you have a document or you have some collection of instances, you want to partition them into k clusters. So I am giving document as an example, it just becomes easier to relate. So you could do the following, you could minimize intra-cluster distance, right? All your, let's say all your project reports, how do I cluster? So I have D1 to Dk are, let's say, your project reports, right? Let's say they are the eventual CS337 project reports. So you might minimize the intra-cluster distance while also maximizing the intra-cluster semblance. I mean, you can do either of them. Make the similarity within a cluster very high or minimize the distance between points in the cluster. So that's the first point. And so that's how rho and delta are used. Both of those correspond to the black choice we have written, high rho, low delta. Right? This is saying that high rho and this is about low delta. And if you are able to represent a cluster already, if you know, now this is a very important point, what represents a cluster? Is it a single point? Is it an average of all the points that sit in the cluster? So these are cluster representatives. I gave you the example of the dendrogram, and there I said, well, possibly every example counts as a representative. So when you do complete linkage, it says every example should be close or far away, right? Or max should be as small as possible. So, but typically what you want to do is actually develop a representative for the cluster and not look at every point in the cluster. It just becomes too expensive. So if your cluster representations DIs are available, then you may also want to minimize the delta with respect to the representative, that is minimize the distance from the cluster representative. This is what it is doing. Or you might maximize similarity. With respect to the cluster representative. There is one more choice you can have. When a point gets assigned, a red point gets assigned to a cluster, green cluster, or to a blue cluster representative, how much should it be assigned? Small, large, right? So does every red point belong to the cluster to the same extent, or there is a difference in the degree? That's also a confidence score. Okay, so let's just quickly do this top-down clustering, which is very easy, which is what you will be implementing. These are all options I talked about, but now the concrete algorithm. So idea is you partition the documents, partition the set of instances into k clusters. As I said, you can have a hard or a soft. Thankfully, we made the soft part optional. This is a task 3, which is optional, the soft part. The hard part is a task 2. I mean, I didn't mean the task is hard, but it's based on hard assignment, right? This is task 2. So what this hard means is that every point belongs or does not belong. To a cluster. Okay, so there is no kind of degree of membership, whereas soft says that, well, there is a degree of membership associated. A point can belong to small degree or larger degree. Every point has a degree of contribution to a cluster. So they have fractional scores. So when do you terminate this entire process, the process of top down or move to nearest? When assignment ceases to change. There is not much change at all, everything is now kind of stabilized, or the cluster centroids move negligibly over iterations. Okay, so I mean, let me just do this exercise on board. So let's say these are the points. Okay, please participate with me in this small exercise. Now let's say I initialize my centers here. These are my two centers. What would happen? I initialize them there. The points are completely lost. I mean, these are not really reasonable initializations. Initialization should be somewhere close to the points. But let's say I do this. What will happen next? Intuitively, what should you do? I will assign points to the clusters. I will say, okay, you belong here, you belong here, right? I will do the membership. Once I have the membership, so more or less the membership will agree with what I have. Now what will I do next? I will say, well, I mean, you are lying too far away. Let me now choose a new representative. So the next step, so this is step 1, identifying the membership. Step 2 would be pulling the cluster representatives, say as a mean of all the points in that cluster. Okay, so that's the iteration, that's the iterative process. Okay, so overall the hard k-means says choose k arbitrary centroids, assign each document or each instance to the nearest centroid, and then recompute centroid. That's it, that's the basic algorithm. I mean, if you understand the spirit of this, you can go ahead and implement the second task. So this is hard k-means. Now soft k-means says that I could have a membership assigned. I don't break close ties between document assignments to clusters. Don't make documents contribute to a single cluster which wins narrowly. So membership can be, for example, the points sitting on the periphery here, they may contribute to both the clusters equally, they may belong to both. Whereas points here almost unilaterally subscribe to one cluster, right? But soft k-means says that, well, I am going to update a cluster centroid with some membership. Okay, so again, if you are interested, look at it, but there are multiple ways you can contribute. Since it is not part of your exact assignment, I won't go over it right now. How do you find the k clusters? So one thing you can do is, you can do the following, you can actually do this bottom up. The bottom up is interesting because it doesn't, I mean, look at this bottom up clustering here, and this may be useful to your assignment. The beauty about bottom up is I don't decide beforehand what the value of k should be, what those k cluster centroids should be. I let the data kind of evolve, right? Now this might be helpful in determining the initialization of the k cluster centroids. So I can keep doing this, and at some point, okay, when there are k such groups, I might just cut it off and say, well, let me start my k cluster centroids from here and then do top down clustering. Okay, so for example, you may randomly sample some root kn documents, run bottom up group average clustering to reduce to k groups or clusters. So that will take order of k and log n time, and then thereafter move every document to nearest cluster. If you want to do top down, your question is, why do you even want to do top down? Yeah, but it may not satisfy the criterion that top down wants. See, top down has a notion of a cluster representative, bottom up doesn't have a cluster representative. So it's just peer to peer, right? Pairwise similarity. So there is a kind of bias, and you are trying to bring in that bias, which is often useful. Okay. So yeah, you can actually seed the K clusters. So this is interesting. This is how bottom up can seed top down. And what should be the value of K? Is generally problem driven. It should be, can be data driven only when data is not sparse, right? I mean generally it should be problem driven. I mean as I said below, I mean I know this is income data, I roughly know the number of clusters, what I expect. But if the data is not sparse at all, I mean it's too thick, then you may want to decide, well, let the data tell me how many clusters I should have. But that's not very often the case. And often it's done interactively. So often you look at the clusters then and kind of then decide, no, okay, 5 is too many, I should have reduced it to 3, and I'll just show you a demo of this. So then there are also more principled approaches. I'm marking this as optional, but in case you are doing, you're taking your assignment too seriously, I mean nothing wrong in trying these out. You can also do proper hypothesis testing. You have done hypothesis testing in your CS 215? No, okay. So hypothesis testing is like I have an hypothesis that the mean of a distribution is greater than say 0.5. Can you reject my hypothesis in a proper probabilistic setting? Okay, so you can do that. And the null hypothesis there is underlying density is a mixture of K distributions. Are you able to refute that hypothesis? So as I said, this is really optional. And then Bayesian estimation has also been used. I mean whatever we have been doing, the Bayesian framework has also been used for choosing the value of K. So this is the exact K-means algorithm, a hard K-means algorithm, a hard EM. So initialize each cluster mean to a different random variable, compute cluster memberships that minimizes sum of square distance of points to existing centroids. So that membership is 0, 1, but instead it could have been a probability distribution, something between 0 and 1, a posterior, compute the cluster centroid that minimizes sum of square distance of points to the centroid. This is the basic idea. So if the parameters have changed after one round of clustering, increment t by 1 and go to the next round. And what does each of those steps mean? Right. So for example, to find the cluster memberships, all you have to do is pick the cluster centroid which is closest. You can show that this choice, choosing the closest cluster center, will actually minimize the sum of squared error. And likewise, once you have computed the membership, new membership, just computing the mean for that cluster can be shown to again minimize the sum of squared distances. So that's it. So this is the K-means algorithm. Okay, I just wanted to show you this, what it means to choose the right number of clusters. This might be helpful in your assignment. Okay, so here you see 100 points and I have chosen 2 cluster centers, one here and one here. Does it look like a good choice of initial cluster centers? I mean these are initial. Now if you did bottom up clustering, probably you would have got some better cluster centers, maybe one here and one here, but that's okay. So this is where you begin. So I will send you the link, you can try it out. But what I want to impress upon you is the number of cluster centers can be a subjective choice. You might want to inspect the output and revise your number of basically initialization of cluster centers as well as the number of clusters. That's a typical problem with unsupervised learning, and till date basically people get quite irritated with I mean all these, as I call, the black magic involved in getting unsupervised methods to work. So if you are frustrated, then you are not alone. There are many others who will give you company. That's it.